Okay, ladies and gentlemen, let us learn to solve first-order linear equations. And what the heck, I'm going to tack another word in here just for the beginning of this.
First-order linear equations?
We're going to learn to solve the extremely limited set of first-order linear homogeneous equations first. And then later I'll take away the word homogeneous and we can solve first-order linear equations. Maybe. Okay? So what I mean by a first-order linear equation is something that looks like first order, right? Which means there is what?
First derivative?
Yeah, there's a first derivative somewhere. And then what else could there be?
X.
Yeah, there could be a function of x and y, and maybe a function of x times a y. And then this could be equal to something, right? Okay, and the homogeneous part is that I'm going to assume that this is equal to 0. Okay? A similar form, which would be the non-homogeneous part, would be y prime plus p of x y equals,
Q of x?
yeah, at worst you could have some function of x. The book uses f of x, so that's what I'm doing. I'm trying to make my notation match the book on this. So if I flip back into some other notation, yell at me.
Is it linear? Just a quick question. Is it linear out of simplification or is it strictly linear?
Good question.
Because I know that there's like, you can do some, if you take the square root of quadratic, it's kind of acting like it's linear.
Yeah, so this is things that can be rewritten possibly into this form. Does that make sense? So if you can't rewrite it into this form, it's not linear. But you might have to rewrite it. Does that make sense? Okay. So let me add a caveat to this, which is the same kind of note that Manu was just wondering about it. We should note that what solves this really obviously in a really dumb and not useful way. Yeah, when y is 0, right? Like if the function y of x trivially solves this, like this solves every single first order linear homogeneous equation, right? Do not tell me about this solution. This is not interesting. It's a good thing to remember, right? But it will not be interesting to us basically any times at all. So I want you to note also, maybe I should introduce a little notation that your book doesn't use because it'll be convenient later. If I want to say that a function is 0 all the time, I'm going to use this triple equals. That's like y of x is strongly equal to 0. Like, you're not trying to solve for x here. You guys see that? Like, this literally just means the function y is actually 0 all the time. Not, when is the function y 0? You guys see that? Okay. So, and this thing is called the trivial solution. Cool. So if I have a solution that is not y is identically 0, what would I call that? A non-trivial solution. And to save myself a bunch of time, I want to state up front that I do not want you to tell me about the trivial solutions. Okay? So when I write solve this differential equation, I want it to be understood that I mean in a non-trivial way. Cool? And don't think I'll forget there's a recording of me saying this and all of you being like, ha ha ha, of course. Cool? Okay. Let's see. There's also a slight note on intervals that I should worry about. Which I'm going to call, these intervals are the appropriate ones, right? So if, for instance, you had some equation that had a little rearranging required, like a of x y prime plus b of x y. Oops, I probably should remove the dependence on x there, equals f of x. Okay. Which points would I know cause weirdness? Like, I just want to first out the gate, before we get started, I just want to say, like, there are going to be some points that are going to cause problems. I've already seen a couple of those, right? Like, I just want to get it out of the way so it's stated early which points are going to cause me problems. Or, better yet, which intervals will be convenient for me. Like, when is my solution that I generate actually going to work?
When f of x is not 0.
A of x not equal to 0.
Yeah, when a isn't 0. Does that make sense? Because when a is 0, right, then this isn't a differential equation anymore. Right? Another way to think is when you try to rearrange it into this, your form for your first order linear homogeneous equation, you're going to divide by a, right?
Oh, gosh.
You guys all see that? Probably best not to divide by 0, right? So appropriate intervals are going to include the caveat a of x shouldn't be 0. Right? What else are they going to need? So this is one we saw, right? We had that thing where we made a onesie out of something earlier, and we're like, I don't know, maybe, like, sometimes that's 1, but not if the bottom's 0. Like, that was this guy happening.
B of x couldn't be 0 either, because you can't derive 0. Or, no. I guess y can't be 0. You can't derive 0.
Sure you can. Derivative of 0 is 0.
Oh, okay.
Right, it's flat. It's the x-axis. What's a tangent line to the x-axis? The x-axis. Right? How about this? How about I probably ought to require that A, B, and F all be at least continuous. Does that make sense? Yeah, exactly. Right? I would like y prime to make sense. Like, I would like it to make sense that I could differentiate this thing. To ensure that I have a good chance of differentiating things, I'm going to also say that probably A, B, and F should be continuous. Does that kind of make sense? So this is like the very rough blush of where your solution is going to work. If you have A, B, or F not continuous, you better worry about that point. You guys with me on that? If you have A equal to 0 somewhere, better worry about that point. Your differential equation is probably not going to be solvable there. Or at least it's not going to have the same solution you would think it does. You guys cool with that? Yeah, it has to be a little smooth, right? Cool with this? Okay. Let's try solving the easiest differential equation I can think of off the top of my head. Right? So does y prime equals 3x squared fall into, does it fall into the form that I advertised? Is it a first order linear homogeneous equation?
Oh, why not?
There's
What
no
if the B
y
of x
for your
is 0?
square.
Okay, so if I subtract the 3x squared to the other side, right? Then what's your claim?
Then you get your p of x, but you don't have the y.
Yeah, but you don't have the y. So that thing's not your p, that's your
F.
f, right? You guys see that? So this thing is first order,
Non-homogeneous.
right? Is it linear at least?
No.
Does it fit into this form?
Yeah.
Did we say that P has to actually not be zero there?
I didn't say that.
Okay, so then it's close.
Yeah, P is allowed to be identically 0. P should be that kind of, it's B over F, right?
Yeah.
But it's continuous, right? Or, sorry, B over A, rather. It's still continuous because it's still the 0 function. You guys with me on that? Okay, so this is first order. It's linear, but it fails to be homogeneous. Can I solve it anyway?
Let's give it a shot.
Think we can probably manage this one anyways. And it's going to highlight a useful feature without being too confusing. So what's the solution to y prime equals 3x squared?
Y is x cubed.
Plus C.
Oh, okay, so the C was the thing I wanted to highlight here, right? Because a solution, right, is x cubed.
General solution is
A general solution has this constant here, right? And this constant is sometimes referred to as a parameter.
It's like parameters are like things that you can change, but they're not like variables, but they push the function forward or backwards.
Yeah. This one, up or down. Okay.
Yeah.
This is vertical shifts, right, of x cubed solve this. Why is it unsurprising that I have a whole family of things like this? What did I have to start with? Like, what is this thing? What's this information about? Yeah, it's information about slopes of tangent lines, right? Okay, so you know about slopes of tangent lines. Do you know anything about the height at which those slopes take place? No, you know about where they take place in terms of x, right? But you don't know anything about the height. You guys kind of with me on that? So that's why I end up with, what would you call this whole business? Yeah, you'd call this a general solution, right? And that general solution is something sometimes described as a one parameter family. Right, because it's not one function. It's a whole mess of functions that have one parameter that wanders you through them. You guys all see that? Questions on the vocab?
So I understand why it's first order and non-homogeneous and all that stuff. Why is it linear for working with quadratics and cubics?
Good. Because the linear and the first order are both things about the derivatives, not about the x function.
But the derivative is 3x squared.
Yeah, so the derivative is 3x squared. This equation, right, in differential equations land, is a first order and linear equation in differentials. That make sense?
So it's like you're applying the rules of polynomials to the prime, or to the y's and the y prime.
So you're saying that because basically the y prime is the first power. That it's like,
Yeah, so I'm thinking about this. I'm not thinking about this as a polynomial in x's. I'm thinking about it as a polynomial in dx's.
So,
Right, so it's the powers of the derivatives that make things order, right, and linear or nonlinear.
okay.
Do you guys want some more examples of linear and nonlinear things? Would that help? What's
So
that?
would like y double prime be quadratic or just nonlinear then?
Okay, so y double prime equals 17.
Sure.
Whatever, right? Like some stuff. So y double prime equals 17 log x would be, if this was a polynomial in x, right? Well, first, it's not a polynomial in x, right? So at best, it would be infinite order because I'd write a Taylor series for the natural log, right? You remember how to do that?
Yeah.
Liars. Okay. Should we make that the quiz thing? Just to see.
No.
You can
That's
see.
what I thought.
Yeah.
Okay, so this thing's just fundamentally not a polynomial in X land, right?
Yeah.
So what I'm wondering is this thing a polynomial in derivative land? So like, that's me thinking about this thing as kind of the categorical equivalent of a number, right?
Yeah.
Like that thing's a function of X. Right? And then how about this guy? Well, that's y double prime, right? What's the coefficient on y double prime?
That's second order.
Yeah, in this case it's 1, right? So this is second order, because there's a double prime. And it's linear. That is true. And the reason it's linear is that there's just derivatives and y's in each piece. Right? Like this guy's made out of 2 derivatives and a y, and this guy's made out of no derivatives. You guys with me on that? And no y's. Hence the me saying, that one's like the constant term. Right? Because there's no derivatives and no y's. There's no variables in it.
So if we had 17 natural log of y, then that would be nonlinear, right?
Okay, so if I had y double prime equals 17 natural log of y, yeah, this would be a major problem. This is nonlinear. You guys see why? Because I fed the y into a natural log, right? So I have no longer just bare y's kicking around. I have a function of y. This thing is second order
Definitely not.
and non-linear. You guys follow that? Okay, other ways to make things nonlinear? I think we had this one the other day. You guys remember this?
Yeah. Well,
What order is this? Yeah, this would be second order, also nonlinear. You guys all good with that? Okay, what if I had x, y double prime equals y prime plus log of 17?
That looks like a second order linear.
Yeah, this thing is second order linear. The x, right, is playing the role of kind of constants, right? You're like, okay, if I thought about everything in x's as constants, and then all I cared about was the derivatives as my variable, and then I put these y's kicking around, yeah, you would get this kind of thing. Sorry, the derivatives are like the powers, right, and the y's are the
Yeah.
variable. So this is second order and linear. You guys all good with these? Does this help a
When
little
we
bit?
had that, but we had x, y double prime squared.
Why not?
Like this?
Then that's not.
Equals y prime, say? Yeah, this is now,
Second order is not.
it's second order still, but now it's not linear.
So, okay. So if any of the y type stuff is multiplied by itself, then it's not.
Yeah, that's a fair way to say it. If there are y's, yeah. If there's y stuff multiplied together, it's not linear. Cool? Questions, Steele?
If just the x was squared.
If just the x was squared, you'd be fine, it'd be linear. It's because that y prime is in, that y double prime is in there that I'm having trouble.
Just out of curiosity, could you actually solve any of this?
Yeah.
Are we gonna solve those?
We're going to solve this one and that one. The second order linear ones we're going to learn to solve. Off the top of my head, this one's probably doable. This one's a giant pain in the ass. This one might be okay. I I think that would probably be the roughest of them. So I will teach you a technique by which you could get an approximate solution for all of these. Okay. But as far as getting an exact solution goes, these two will solve exactly. This one I think you probably could.
But
You fiddled with it.
They all have closed form, like, they all have a closed solution?
These two I'm not sure.
Okay.
I'll teach you a trick by which we could, by which we could get a really good approximation. I'm not sure if those have closed forms. Differential equations is one of those things that goes all the way down. Like this is a rabbit hole. You can make up little examples, and for a long time in the early 19th century, there were many PhD theses written on solving differential equations of the form blah blah who's it. And they still show up sometimes. Like sometimes it'll still matter. And nowadays the only times they actually appear in journals, or the only times people get PhDs for solving differential equations, are when there's some kind of meaningful interpretation. Like you work with a biologist and they write a differential equation that does something with CRISPR or something. And then if you can solve the differential equation that shows up in that stuff, then it might be interesting to write a paper called Solving Differential Equations of the Form blah, 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 which have uses in field.
So just solving a novel form isn't enough anymore?
It's boring because we have computers now. Like in the 19th century, it was a big deal if you could solve some of these, because there were fluid dynamics problems, for instance, that people wanted to solve, that they had really specific differential equations that came up, and oftentimes they couldn't solve them. But with computers nowadays, like you just cram it in, get an approximation, and move on with your life. Especially in engineering land, right?